step 1 and step 2?
Yeah. Okay, so the concentration would change significantly if, if they don't round. If they round to the same concentration, then that's close enough. It wouldn't perturb. But if step 2, the concentration comes out significantly different, it doesn't even have to be step 2. It could be step 3 or something that perturbs. And so you just look. If
Did you say that they're always supposed to step down in size or magnitude or whatever as they go down the steps?
Yeah, in general, when you're looking at something like a polyprotic or a polybasic, then it would go down in steps. But when we get to more complicated mixtures, like this one, I didn't finish this problem in class when we did this. But if we look at like potassium aluminum sulfate, then what we're going to do is this. We're going to do, let's say, the Ka for aluminum first. This is a pretty big Ka. And so we set up the, the ice table. Aluminum, H2O 6, 3 plus H2O liquid. So we set up the ice table and we get some hydronium at equilibrium here. Then we do the sulfate. And we do the Kb for sulfate. And the Kb for sulfate is going to generate some sulfate's a dibasic base. Well, if it's a dibasic base, we don't just have Kb1, but we also have Kb2. Yeah, you determine it from the charge. I mean, it's 2 minus, so it's going to accept 2 protons, right? 3 minus would be tribasic base. So you just look at the charge and you can tell. And so here, to answer your question, John, here I wouldn't consider the second step, because the second step would be pretty much a minor contributor, especially when you look at the magnitude of the Kb. Because if we look at Kb1, right? Kb1, what is the Kb value for this? The Kb value is going to be Kw over Ka for, not for sulfuric acid. A lot of people are saying it's sulfuric acid is conjugate acid. No, sulfuric acid is not the conjugate acid. The conjugate acid is HSO4 minus. And the conjugate acid, so it's 1.0 times 10 to the minus 14 divided by 0.011. And so this is going to be like 10 to the minus 12, right? And then if we go to Kb2, Kb2 is going to be HSO4 minus. Now, HSO4 minus is the conjugate base of HSO4 minus is the conjugate base of
Sulfate.
No. This is the way you figure it out. If it's a base, bases do what? Bases accept a proton. If HSO4 minus accepts a proton, then it forms H2SO4. So that's the conjugate acid. And so this is the conjugate base of H2SO4. Well, the conjugate base of the strong acids like chloride, iodide, bromide, nitrate, all those are conjugate bases of strong acids. Are those very basic at all? No, we consider them so weak that they're neutral. And in fact, this is going to be so weak that it's going to be neutral as far as base properties go. However, HSO4 minus is amphoteric, and it's much better acid than it is base, but here we're just considering its base properties. If we were to look at Kb2 here, Kb2 is going to be Kw over the Ka for what acid? H2SO4. The Ka for H2SO4 is very large. That means Kb2 must be very small. Well, the Kb2 is very small. We aren't even going to bother, right? Because it's going to be a negligible hydroxide contributor. I have $200 worth of burette here. But actually, this is volumetric. This is about $200 worth of volumetric too. Put that
Are
in
you demonstrating
Knock it
something?
over. What's that?
Are you demonstrating a
No, I'm not demonstrating, but somebody else is demonstrating. I just don't want to knock it over by accident. So in this case, the second step is negligible, right? Compared to each successive step becomes negligible. But when we have complicated equilibria happening, well, we have another step here. And the other step would be water, Kw. And so here, it's not necessarily negligible because Kw is a different equilibrium. And if we look at Kw here, Kw is going to be this. It's going to be H2O liquid plus H2O liquid. This gives us hydronium and hydroxide. All right, and so what we could do is if you decided, actually you wouldn't have even been able to do step 2 here because we don't have the K value. You know, it's very small. So what we're going to do is we take the hydroxide generated from this and we plug it in here. And then we take the hydronium generated from this and plug it in here, right? And then you either do this, you do a Le Chat liaise. You know, here's your initial, and so we're going to see that this is going to shift left or right, depending on what Q is, right? And it turns out that Q is going to be greater than K. Actually, we did the numbers for this already, right? I just didn't do the last step. Do you have it in your notes? Just complete this last step. What did we get for the hydronium from aluminum? 3+. What was it? 1.48? 1.18 times 10 to the minus?
Wait, for the hydronium?
For the hydronium concentration.
Yeah, I got 1.8 times 10 to the negative 30.
Times 10 to the negative 30?
Third.
Third, oh, okay.
Yeah.
Whoa.
Sorry.
Yeah, sorry. So, you know, the pH is around 3 or 4. pH 3 or 4, this is pretty acidic, right? That's pretty acidic. What was the hydroxide from this step?
I think it's definitely aluminum. It's 9.09 times 10 to the negative 13.
Is that KB or
Oh, sorry, yeah, that's just
did we?
that's your game.
Yeah, we finished this calculation, didn't we?
No, I'm taking this from the lab stuff.
Oh, you took it from the lab. Did we do this in class?
This was the part of the pre-lab calculations for the.
All right. We didn't do potassium aluminum sulfate at all?
We have the HSO for
Yeah, you did the.
we did
Ammonium acetate? Oh, okay, we did ammonium acetate. I didn't do aluminum sulfate. But ammonium acetate is the same thing, right?
Yeah.
Well, anyway, we could do this. This won't take very long then. The KB for this is 9.09 times 10 to the minus 13. All right, and so when we set up the ice table for this, this was going to be, what was it, 0.100 molar? So this will be 0.200 molar, right? This was 0.100 molar. Is this right then for 0.100 molar? All right. So this is 0.200 molar water out there. This is 0 molar. This is 0 molar. So minus X plus X plus X.
Okay, it's 0.200 molar because there's 2 sulfates?
Yeah. So we can get this. This is 9.09 times 10 to the minus 13. It's very small. This is going to equal x squared over 0.200 minus x. The SA should work here, no problem. a fairly high initial concentration in the K is small. And what does X come out to?
I got 4.24, and that's all my digits, times 10 to the negative 1, 2, 3, 4, 5, 6, 7.
Times 10 to the negative 1?
7.
Times 10 to the negative 7?
Yeah.
Okay.
4.24.
4.24 times 10 to the negative 7 molar.
Yeah.
And 1.18 times 10 to the minus 3 molar. And so, you know, this hydronium and hydroxide exist in the same solution, and so Kw has to be maintained here. And so if we drop these concentrations down to Kw, we get 1.18 times 10 to the minus 3, and then 4.24 times 10 to the minus 7.
Okay, why do you have to consider KW?
Any aqueous solution, we have to consider Kw because you can't stop reaction from occurring. You know, they're going to be collisions. If the hydroxide and hydronium ion concentration increase, then there's going to be reverse reaction to form water, right? Countering that reverse reaction is the forward reaction between the collisions of the water. But right now we got too much hydronium and hydroxide to sustain. Do you see that Q is going to be greater than K? I mean, 10 minus 3, 10 minus 7 is like 10 minus 10, something like that. 10 minus 10 is a lot bigger than 10 minus 14, so it's going to, we got too much hydronium and hydroxide, so we're going to lose. We're going to minus X and minus
Minus X and minus X.
yeah, minus X and minus X. But you know, this is what, you know, back in, I don't know what chapter it was. Back a while back, I said that this is a Le Chatelier's type ice problem. The Le Chatelier's ice problem is you're going to end up with two binomials here. And so to avoid this kind of Le Chatelier shift, I just said, well, why not just reset it? Resetting is going to be easier, so I don't solve it Le Chatelier's, otherwise, well, let's set it up and I'll just show you why. Times 10 to the minus 3 minus X. 4.24 times 10 to the minus 7 minus X. This is why I don't set it up Le Chatelier's, because one, it's going to be 1.18 times 10 to the minus 3 minus X. You know, to get points, extra points, you should do this, H3O plus. In case you make a mistake, you should show me the expression, because I can give you partial credit, at least if you get the expression right. Rather than just jump straight to this. Okay, the reason why we reset is, number one, can I use the simplifying assumption here? No, because X would drop out of both and I can't solve it for X, right? And so, one, I can't use the simplifying assumption, and two, I got, you know, two binomials.
Would
And
that
so-
solve through quadratic if you kept going?
Yeah, I'd have to solve this quadratic, but you know, multiplying these out is a pain. And then keeping track of the digits and everything else is just a hassle. And so people ask me, why do you reset? Well, this is one of the reasons why I reset, to make the math easier. And this is a strategy that we use because it doesn't matter. You know, technically, you know, this is a Le Chatelier's on a Le Chatelier's, because technically I should be starting with 1.0 times 10 to the minus 7, 1.0 times 10 to the minus 7, and then add these two to those, and then do a Le Chatelier's shift, right? But I already reset it. Your book is automatically going to reset it to 0 and 0, otherwise it becomes too much. And so we always reset. Your book even resets. It's just the easiest way to solve these. And so we reset this, and then we get the new initial. Well, which one's the limiting reagent here? It's going to be this one, right? And so the hydroxide is going to go to 0 molar, and then it's going to be, it's a 1-to-1, so we're going to lose 424. And so let's get this in times 10 minus 3, so I need to move the decimal. Well, actually, I just like to write it out so I don't make mistakes. 118 minus 6 zeros. 1, 2, 3, 4, 5, 6, 4, 2, 4. Got some more zeros here. And so tens is going to be 6, 7, 5, 9, 7, 1, 1, 0, 0, 0. All right, and so these are my reset initial conditions here. And so here the change is easy. It's just plus x molar, and then at equilibrium, 0.00117956 plus x. The reason I like to carry so many extra digits is because I like to avoid round off, because when you do the double check, it's always disconcerting if it's off, and you don't know why it's off. If it's off because of rounding, this just saves time. It saves time in the long run, because if you carry extra digits and your k's right on, then good, you can continue. But if it's off, then you have to start thinking, did I make a subtraction error or calculation error or something like that? And,
okay, how do you get the initial to be 0.00186000?
Yeah, I just shifted these. I just said I don't want to deal with that. I'm going to just reset this to the left. And so I assume 100% reverse reaction. Well, that's going to consume the limiting reagent here. And so I just took this minus that. Punch it out in your calculator, and hopefully it comes out the same. There. And so the K here is going to be 0.0011. You don't have to carry this many digits, 5, 7, 6, this is overkill, plus x times x. And here the simplifying assumption should work no problem, right, because it's fairly large. So we use the simplifying assumption here, 1179576 times x, and then x is equal to what?
Water.
KW, yeah, this is KW, 1.0 times 10 minus 14. 8.77 times 10 to the negative 12. Okay, thanks. And so this would be the hydronium ion concentration here. This is the hydroxide ion concentration in equilibrium. This is the two waters over here, which are liquids. So just omit those from the ice equation here. And so at equilibrium, the hydroxide ion concentration is 8.477 times 10 to the minus 12 molar. And the hydronium ion concentration is, does that add much to this? No, and so it's just going to be the same. That's 11 digits out. That's way out here, so it's not going to change this at all. So insignificant. Insignificant addition of hydronium to the reset, but is significant. And so we double check these. Does this multiply out to 10 to the minus 14? 1.0 times 10 to the minus 14. Yeah, 9.99 times 10 to the minus 15. Times 10 to the minus 15. If we change this to times 10 to the minus 14, that's 0.999 times 10 to the minus 14, which is 1. Pretty much rounds to 1. So this is good. This checks out. I forgot to check this though. We checked the aluminum, right? So let's check this one out to make sure that these numbers are correct. Otherwise, I just wasted a lot of time with that. 4.24 times 10 to the minus 7 molar here. And this is going to be, well, if I have 0.200 minus 10 to the minus 7, is that going to change this much? No, this is going to be about 0.200. And so let's just say about 0.200, just slightly less. And so do these concentrations check out here? Give me a K of 9.09 times 10 to the minus 13. It does? Okay, then we're good. That's good. what was it, 9.8?
8.98.
8.98, 8.98, yeah, that's pretty good. Well, it's because of rounding, most likely. But the more you round, the farther off you are, you know. And so that looks good, right? And so does this check out? So Kelly, does this check out? Does this look good to you? Not only do we want to check out the K's, but we also want to check out one other thing. What's the other thing we want to check out?
Concentration?
Because we did this in stepwise, right?
Mm-hmm.
But is stepwise always valid?
No.
No, so we got to check if stepwise was justified in this particular problem. Is it? And so what do you do if you want to see if stepwise is okay? You don't multiply, we did multiply the K's and everything checks out, right? But there's a problem, though. We check the K's in sequence, right?
Uh-huh.
But this is all in the same beaker. Can you have two different hydronium ion concentrations in the same beaker?
No.
No, so what do you do? Kelly, what do you do?
It perturbs.
Well, no, you have to determine if it perturbs. And how do you determine if it perturbs?
You gotta check the concentration.
Yes, and did the concentration change significantly in going from one step to the next step?
No.
Well, take a look at the hydroxide concentration. The hydroxide's concentration we left off with in step 2 was 4.24 times 10 to the minus 7.
Uh-huh.
And then water consumed, that KW consumed some of that hydroxide. And so we lost about five orders of magnitude, which is 100,000 times or something
That
like that,
really
right?
perturbs. It's significant.
You see, this is a significant change in hydroxide. So what we gotta do is we gotta erase this, right? Because now we have a new hydroxide after step 3. And so this hydroxide is no longer valid. And then we got to plug in this hydroxide back into this and see, does K check out? No, K is going to be 5 orders of magnitude off. Did that perturb?
Yes.
Yeah, and then look at the hydronium. What was the hydronium we left off in step 1 with?
0. Hydronium in step 1.
1.1 times.
10 to
Oh,
the-
then, you know, for hydronium it didn't really perturb, but for hydroxide it really screwed things up, right? And so what does that mean? That means that
we gotta
we
solve
can't
it.
solve this stepwise. We have to solve this simultaneously with all 3 equilibria being solved at once so that the hydronium and hydroxide are valid for each of the 3 equilibria.
Wait,
Uh-huh.
but if hydronium isn't really being perturbed, and you're asking for pH, can you just do it like this?
Okay, if the hydronium isn't really being perturbed and they're asking for pH, can you do it like this? No, you can't do it like this because
pH is the same.
yeah. You know, just because these 2 are okay stepwise, can you ignore this one? Well, that, you know, I shouldn't say no, because there are certain scenarios where you can ignore one equilibria because the K is so small, right? And so the classic example of that is hydroxide. You know, hydroxide's amphoteric, so hydroxide has a Ka and a Kb, but when you look at the Ka for hydroxide, it's so small that people just ignore it, you know, even though it could act as an acid. And so there are scenarios where you could ignore it, you know, but this one, you know, what we have to do is we have to come up with a hydroxide that works for essentially all 3. And since the hydronium and the hydroxide are tied together, when we come up with that hydroxide that works for all 3, that's going to change the hydronium, right? The hydronium can't stay like this. I can't just say, okay, now I'm just going to solve the second or the last two for a hydroxide that works and just ignore, because my hydronium worked before, I want to keep it, so let's ignore that and disconnect it. So that would be like cutting one arm off and then just ignoring that, and then, do you see, but it has to be connected, because the hydroxide will change the hydronium, and that hydroxide does not work. Okay.
So we gotta simultaneously.
Yeah, unfortunately you have to solve this simultaneously, but you know,
So technically for all of them, we would have to solve this simultaneously.
yeah, for all equilibria you're supposed to solve simultaneously. So what we're trying to do is we're trying to see what type of equilibria problems can we solve by hand, and do those. But but we're going to have a lab, Visual Mintac, and then you'll see, wow, it's even when we solve it by hand, you know, we're ignoring certain things like activities and all this other stuff, you know, and so our calculations aren't rigorous enough.
And as far as this test coming up, are we gonna have to worry a lot about that? Because I know the text for the first part of the homework doesn't really worry about it. Sometimes you have polarities to the negative 13, and they'll take into account all the way up to the advanced exercises.
Well, the advanced exercise, did you guys see where they screwed up in the advanced exercise in the solutions manual?
Yeah.
Yeah, where they, where obviously they went from step 1 to step 2, and there was a huge change in the hydronium or a huge change in the hydroxide, and they didn't look if it perturbed the previous. And so they have two different hydroniums in the same solution. One hydronium that works for step 1 and one hydronium that works for step 2. Impossible, right? So that's good, you caught that.
And then I'm talking about the common ion effect until chapter
17. They don't talk about the common ion effect until chapter 17, but you know, the only reason I'm talking about it now is because when you carry something down from step 1 to step 2, it's common ion effect, basically. It's common ion, so. But there are different ways that they do it. The style of common ion effect that they do in chapter 17 is when they add a salt to it to make the common ion. So it's a little bit different. So, well, what do you do in a situation like this? Well, you aren't going to do this by hand, probably. You're just going to use a computer package. And a computer software package like something like Visual Mintac is extremely powerful and free, you know. And actually much better calculation, but we got to learn the techniques, right? We have to learn the techniques so that yeah, so we have an idea of what's happening. Although they use, you know, mass balance. We don't use mass balance in solving equilibria, other things. They have to, because the equilibria get a lot more complicated, a lot more species are involved. So they solve them slightly differently, but you know, it's just learning. This is the basics, and then you learn more advanced as you go along. And so this is just building the foundation. But yeah, essentially every equilibrium problem that there's multiple equilibria like this needs to be solved simultaneously, with some exceptions. The exceptions are the ones we could do stepwise, in which would make no difference if we solved it simultaneously versus stepwise. And the other one is, which we'll talk about, is combined, which we'll see in chapter 18.
But on the test, we don't have time.
Yeah.
You gotta look at the problem and know when to solve simultaneously, right?
Right. And so, you know, we'd be done here. On the test, we'd be done. We'd say, that perturbed it. We got to solve simultaneously, and that's it. That didn't take that much time. Right.
No, like look at it right away and say.
You can't. You can't always look at it right away. You have to. You know. You have to. What we do in our problem-solving approach is we just assume stepwise is going to work, and then determine if it fails. That's all.
So you said Visual Mintac was the one that you would use to get the.
Yeah, Visual Mintac.
So is that what we should do for the pH in the lab?
No, not at all.
I got 2.97.
No, for our lab, what do we do with the pH? We could estimate the pH, you know, like David was saying. We could estimate it, try to take a guess at what the pH is gonna be. And the guess would be that the acid dominates here. The acid dominates because the Ka is kind of big for aluminum, it's 10 to the minus 5, versus sulfate is such a weak base, let's just go ahead and ignore it completely. And then come up with a, you know, the pH is going to come out close, right? And so you're okay with that, but
So that is, that is where you're gonna do that, like you said.
but you have to in other words, you have to qualify your answer, saying that, you know, the pH of this solution is going to be less than 7, right? And if you come up with a calculated number, you're going to say that, well, it's just, you know, a guesstimate, approximate pH, that's all. It's like hydroxide. You know, what's the pH of hydroxide? When you determine the pH of hydroxide, do you ever consider the Ka for hydroxide? Would you do that? No, because you'd say it's so small it's negligible. Well, when is it so small it's negligible? 10 to the minus 13? Maybe, maybe not. Yeah.
Okay, where is this problem in the book? Because I would want to replicate it.
This problem is not in the book.
Wait, it's not in the book?
It's in your lab manual. This problem is in your lab manual. Let's see.
Lab manual?
And the lab manual doesn't actually ask you to calculate the pH. You just use a pH meter. That's all. The only reason I brought up these is because we're talking about weak acid, weak base mixtures. Weak acid, weak base mixtures must be solved simultaneously, unless you have two scenarios. What's a weak acid, weak base mixture can be solved, the pH can be solved if what? If the weak acid and weak base, number one.
I was gonna say don't perturb one another.
No, that's not it. They always perturb one another. A weak acid, weak base mixture can be solved, the pH can be solved quantitatively if one, it's amphoteric. The weak acid and the weak base are the same species. Then we could use the simplified equation that you get from solving it simultaneously. The pH is equal to pKa1 plus pKa2 divided by 2. And scenario 2 is when the weak acid and weak base are conjugates of each other. Then we can use the Henderson-Hasselbalch. That would be a Henderson-Hasselbalch mixture or Henderson-Hasselbalch buffer. Otherwise, if we have a weak acid, weak base mixture, it must be solved simultaneously, right? And so that was the whole point of doing these mixtures for the weak acid, weak bases. The book does talk about it, but it spends all its time on Henderson-Hasselbalch because that's one we can solve. But what about all these others? You know, on a test, you aren't always going to get a Henderson-Hasselbalch, right?
So we just need to have calculations of the number that shows that it's perturbed.
Yeah, right. I'm not going to expect anybody to solve except for extra credit. You know.
Ammonium nitrite, the acidic, basic, or neutral.
For example, that,
Acid base means mixture.
a polybasic base. Did I do a polybasic base?
Is that like a magnesium hydroxide? Not magnesium, but just 2 hydroxide. Is that what you mean?
Yeah, except magnesium hydroxide.
Calcium.
You just talked about it as like sulfate.
Okay, did I talk about sulfate?
Yeah.
All right. Right. Did I do sulfate in class? Just set it up? No. We could do a polybasic base. I did polybasic base in the afternoon class, phosphate. Do you want to do that one really quick? Yeah. All right, why don't you do that one? A polybasic base is just like a Yeah. I didn't do this one. I skipped this one for this class because I was thinking, I need to save some time. Yeah, but I had a little extra time in the afternoon, so I did it in the afternoon.
So Dr.
But do 0.100 molar sodium phosphate.
Set up the
Uh-huh.
valve.
Just set it up. There are gonna be, there are gonna be 4 steps in this. KB1, KB2, KB3, and KW. Yeah, Kelly?
Would ammonium nitrite be basic, acidic, or neutral? Because it's an acid, because it's a weak acid and a weak base mixture.
Right, it's a weak acid, weak base mixture. So ammonium nitrite has to be solved simultaneous, basically. But what we can do is we can guesstimate the pH to different degrees, right? And so we have ammonium nitrite. The way we guesstimate the pH is if Ka and Kb are about equal, then the pH should be about neutral, right? And so we just compare the Ka. The Ka for ammonium is 10 to the minus 10. I mean, what's the Kb for nitrite? And so we look at nitrous acid. What is nitrous acid? It's 10 to the minus 2, 10 to the minus 3. Gavin, you can see that. 10 to the minus 4 for HNO2. 10 to the minus 4, and so that would be 10 to the minus 10. So these are about the same, so it's going to be close to neutral. You know, that's a guesstimate.
But in the solutions manual, it says it's basic.
It's basic, then we have to, it's just going to be, if it's basic, it's just going to be slightly basic. Because we compare. That means that if the solutions manual says it's basic, that means that Kb is greater than Ka, that's all. All right, let's just start on this one. I'll be right back.
They just gotta figure them out.
Down, K,
These are gonna go to here, and then that's
but you're trying to find
what-
Kb, so you gotta find the area of the conjugate of the last.
K-water.
Yes.
So,
Yes.
I have a question. This is having out, if I put H2O on the left and H2NOH on the right, or, because this is all done backwards from the acid base, and like, you usually start out with this plus water, there you go, up that. Right, right, right. Okay. Right, so this one here though will still produce hydroxide.
How do you know if you find Ka or Kb? What we're really looking for? Yes. Yeah. But I got the my equilibrium right there. How come? Is it a certain right? Is there a certain right way? Excuse me. Is there a certain right way to write the equilibrium for this?
Yes.
Why can't we just write it in reverse direction?
You cannot write it, a lot, you know what? A lot of people do this on the test. They write H3PO4 plus H2O liquid. H3O plus H2PO4 minus. But the problem is there's no H3PO4. If we were given H3PO4, then you can write it reverse. for bases, since we don't do that many bases, this is probably why people get confused, because most of the time I spend on acids, Kas, and so I don't do as much for the bases. And so we can't do that. You can't have it. You can't. Yeah, we can't have it because there's no H3PO4. It's PO43 minus. There's a huge difference between H3PO4 and PO43 minus. H3PO4 is highly acidic, pH is very low. PO43 minus is highly basic, pH is very high. In fact, a lot of laundry detergents use it. They call this tribasic, or trisodium phosphate or whatever.
Shampoos use ammonium sulfate.
The shampoos will have lots of different formulations.
Ammonium. Ammonium sulfate's more common.
A lot of people also screw this up. I've given sodium phosphate lots of times on test. There's a lot of people do phosphoric acid because they've seen it before. I did phosphoric acid before. Just write it. And then a lot of people write the Ka for phosphoric acid rather than the Ka for monohydrogen phosphate. Here.
Why do we have to find the Ka for the conjugate acid?
Because I don't give you the KBs. I won't give you, maybe the only KB I might give you is ammonia. So if you don't have the KB, you have to calculate it. I actually don't want to use that one if possible, because that one's not the same as a book. Does somebody have the Ka for monohydrogen phosphate?
Sandra, you have the chart in front of you.
Uh-huh.
On the exam, are you going to
When I gave this problem on the test many years ago, I only gave the Kas. And so there are a whole bunch of mistakes that people made. A lot of people use the Ka instead of the Kb. A lot of people try to use the Kb but miscalculated the Kb because they got the wrong conjugate acid. Just you see every variety of mistake. A lot of people use, like I said, phosphoric acid and then use the Kb. It's just every variation of screw up you can make, I've seen, I think.
4.2 times 10 to the negative 13.
4.2 times 10 to the negative 13?
Yeah, the answer is 0.0238.
0.0238. This is a pretty good base. Phosphate is borderline. If you look at the borderline between hydroxide, sulfide's misplaced in that chart. Sulfide should be more powerful than hydroxide. What's at the border between weak and strong? Phosphate. Phosphate's borderline strong base. pH should be really high on this. And so if you had sodium phosphate in water, it feels slippery, just like sodium hydroxide. Well, anyway, we're going to continue this. So we have 0.100 molar. If we're doing inventory, a lot of people also miss sodium ion because they just went straight to phosphate, and so they didn't tell me what the sodium ion concentration is. The sodium ion concentration, this is why sometimes I'll do another step. The other step I might do is treat sodium phosphate as strong electrolyte soluble salt, and then I'm going to generate what concentration of sodium ion? 0.300. Either you see this or you just write out the equation. It's 0.300, and so they missed the sodium ion in the inventory. Lost the point for that. Okay. And then H2O we got. And so just to save time, this is 0.100 minus x. This is x molar, x molar. So this is going to be x squared, 0.100 minus x. I worry about the simplifying assumption because the K is kind of big here. But even though I worry about it, I don't worry about it so much. I'm just going to use it. And so I'll just get x squared over 0.100. That means x is equal to 0.0487. 48.7% change. Unfortunately, simplifying assumption failed.
Quadratic.
Yeah, so we have to use the quadratic, which is going to be x squared plus 0.0238x minus 0.00238.
Other way around.
There'd be point, yeah.
What is it?
Minus the variable plus the constant.
Oh, yeah, the plus and minus wrong. Yeah, do you?
Uh-oh.
Yeah, the first one would be 0.00238x, and then
And that's the negative.
the last term is 0.0238. It's 0.1 times 0.02.
X squared minus 0.00238x plus 0.0238.
Is it? All right, what is it? X squared minus 0.0238x plus 0.00238.
Yeah.
That's it? Okay. All right, thanks.
How do you evaluate scientific knowledge?
Hmm?
Evaluate.
Is that right?
I'm
No,
gonna
I
get
want
plus x
evaluate.
and then minus constant.
Giving the answer doesn't.
Okay, what is it? X is equal to?
0.033.
X is equal to 0.033. Well, give me one more digit.
383.
383.
83.
Okay.
No, 0.0383.
Oh, 383. Okay. All right. And so this is going to be 0.100 minus 0.0383. That's 38.3% hydrolyzed, which is significant. 0.0617 molar.
Professor, the plus and minus is on that quadratic are backwards. I just checked it again. Wait,
It's plus point, yeah, it's.
it's plus 0.0238 and it's minus 0.00238.
Okay.
That's a plus, and then the next one's a minus. Yeah. That's correct.
All right. Did it change our x value?
No,
Did it? No? Well,
because I calculated it like that.
No, you saw it right. You switched this. You got it right the first time. Or just switch the signs. Because you gotta move the
Okay.
other side of the equation.
Our x value comes out the same?
Well, I calculated it like the right way, so the x should be.
Oh, okay. All right, the x is fine. All right, 0.0383. 0.0383.
that was crazy.
Well, you know what? When we do our double check, we can figure out if it's correct or not. You know, so this is the utility of doing the double check. And so we double check the equilibrium concentrations. Do they check out okay? Okay, then we're good.
When will the quadratics will not work? When
The quadratic always works. We just try to avoid doing the quadratic by making these things.
I know, but if K is
A
190.
quadratic is always going to work, so you don't have to worry. Oh, when the I'll tell you, it doesn't always work. The quadratic will fail if you have, okay, if you have a very big change, the quadratic fails.
You gotta set it.
Yeah, and so what happens is, let's say you started off with 0.100,
Uh-huh.
and the change is 0.9999999. How many digits is that? Like 7 or 8, 999? Then the quadratic is going to fail because your calculator doesn't carry that many digits. and the quadratic fails. That's why you have to
Reset.
yeah, to make it a small change. But you know, those are things that you don't know when, it just happens, and then you got to try to fix it. So I don't worry about it. Is it going to fail or is it not going to fail? Because that's kind of a waste of time. You're just guessing. If you can't solve it, then you start trying to do tricks in order to get the answer, get the right answer. So don't worry about when it's going to fail or not fail. It'll fail, and then you'll realize it failed. So what do you do? All right, this is a polybasic base. So the next step is this, HPO4 2-, but HPO4 2- is amphoteric, right? So if it's amphoteric, then that has a Ka and a Kb. So what should we do next? Because we have some of this amphoteric species. Should we do the Ka for HPO4 2- or the Kb for HPO4? We need to do Kb, and then we should do the Ka, right?
Wait, I thought it would be redundant.
You thought right, because we don't need to worry about the Kb. We don't need to worry about the Kb because we just did it in step 1, right? And so in base solutions, the simple answer is you just look for hydroxide producers. So the next hydroxide producer is going to be HPO4 2-. We already took care of phosphate. And so the next one will be HPO4 2-, which can collide with water to form H2PO4- and some additional hydroxide. Yeah, and so we just bring down this. This is the common ion effect, right? The common ion effect is this. We're going to have 0.0383 molar HPO4 2-, 0 molar dihydrogen phosphate, but we don't have 0 molar hydroxide. If we had 0 molar hydroxide, this would just hydrolyze as it normally does hydrolyze. But now we have a lot of hydroxide present. This lot of hydroxide acts as kind of like a predator, you know? That means we can't form, the population of H2PO4- cannot grow too big because we got too much hydroxide here attacking it. This is the common ion effect. So common ion effect is, why did I start talking about it in chapter 16 and not wait until chapter 17? Because I thought, why wait? You know, we're dealing with it now. The only thing is in chapter 17, you would have put some acid in here and then you would have sprinkled the common ion in there. But this one, I mean, it's the same, essentially the same thing, which means that X, you know, the change is typically small with the common ion effect. So 0.0383 minus X, X, 0.0383 plus X. And then Kb for this, and you should write out the expression on the test, you know, H2PO4- times hydroxide divided by HPO4 2-. If you get the answer right and you didn't write this, I'm not going to deduct anything, but if you got the answer wrong and at least you wrote this and it's correct, then I'll give you more partial credit. So that's the strategy behind that. And so this is going to be X times 0.0383 plus X divided by 0.0383 minus X. Here, you know, I don't really worry about it. I just go ahead and use the simplifying assumption. You know, is it going to work? Is it not going to work? Should I calculate the...
It's like 100%. You check it.
Okay. And so, yeah, the X is going to, well, equal Kb. Did we calculate Kb? Kb is going to be Kw divided by the Ka for what acid?
H2PO.
Yeah, H2PO4-.
1.58 times 10 to the negative 7.
Well, 1.58 times 10 to the negative 7 thing. So the percent change is very small. This is 10 to the minus 2. You know, this is 10 to the minus 7. 10 to the minus 7 over 10 to the minus 2 would be 10 to the fifth times 10 to the minus 2. 10 to the, this is a very small percentage. And so the simplifying assumption would be okay. It checks out. Now, we plug that in here, so this is gonna be about 0.0383.
2 zeros and 1 5.
2 zeros and 1 5. Oh, thanks. This is going to be 1.58 times 10 to the minus 7 molar. This is going to be 0.0382985 molar. Then we would double check those concentrations to make sure the K is okay. Are the Ks okay? Does K check out? Oh yeah, minus, you're right, 29985.
The other one,
383
001.
Yeah, you know, the only reason I carry that many digits out is just to show the significance of the change, but you don't have to carry that many digits. You can carry at least 1 or 2 digits past, right? That's enough. This is not a Henderson. This one, all right. Yeah. This would be kind of like a Henderson-Hasselbalch, but the problem is we have the other stuff in there, and so that makes it a more complicated mixture. A Henderson-Hasselbalch would just be this and this. Okay. This would also be a Henderson-Hasselbalch, just this and this. But the situation is, Henderson-Hasselbalch depends on what we start with. And in this case, we only started with phosphate. If we started with phosphate and monohydrogen phosphate, that would be Henderson-Hasselbalch. We have to have significant concentrations of both the weak acid and the weak base initially to be considered, because this is not a mixture of a weak acid and weak base. This is just a mixture of base. That's it. So this is the difference between chapter 16 and 17 also. In 17 we're looking at acid-base mixtures. Did it check out? Okay, then we would look for, did this step perturb the previous step? So this is why I carry out so many digits. Did the, if I didn't carry out so many digits, sometimes it's hard to see, but did the monohydrogen phosphate concentration change significantly?
No.
Did the hydroxide ion concentration change significantly? No, so we're okay. This is okay for stepwise. So do you see, then we'd have a step 3 and a step 4. Do we need to go through those, or can we skip those?
The KB3 is 1.408 times 10 to the
Yeah,
negative 12.
yeah. If we're looking for hydroxide, if we were looking for the pH, I would have stopped at step 1. If I'm looking for the concentrations of all the species, the inventory, I would do all 4 steps. But basically, the process is the same. A polybasic base is the same process as a protic acid.
You just have to find the KB.
Right, to find the KB, and it's base plus water yields hydroxide rather than acid plus water yields hydronium. That's all. All right. Huh?
You know how you hydrolyze the water? You make hydroxide.
You basify it.
No, this is called hydrolysis.
Oh, that is
Hydrolysis is breaking apart water.
either way.
Either way, there's 2 ways to break apart water. Essentially, so that's it. Both of these are hydrolysis. Ka is acid hydrolysis, Kb is base hydrolysis. And in other words, it's always, Ka is always acid plus water. Kb is always base plus water. You have to memorize that, because when we get to mixtures, then we don't always have acid plus water. We have acid plus base. Well, water is a base. Did I talk about very large, very, very large, and very, very, very large?
Mm-hmm.
Yeah. Okay. All right, so this is how you set it up, and then you just continue as you would normally, you know, step 3, etc. I'll just write etc. All right, so let's go back to our chapter 17 stuff. Unless, is there anything else from chapter 16?
How extensive is the Lewis acid bases on the test?
Lewis acid bases on the test will be. Do you know the definition of a Lewis acid base?
Proton acceptor, proton, or sorry, electron pair acceptor.
Yeah. Did you read that last section on Lewis acid bases in the book? What else did they cover?
Hard, soft.
Did they cover hard soft? I want you to know hard soft. But did they cover hard soft in the book? No. And so what you should know is this. All acids, true or false, all acids in nature are Bronsted acids. That's false. How about this? All acids in nature are Lewis acids. All acids in nature are Lewis acids. True or false?
True.
True. You know, and so we only need one definition for what an acid and base is. The only definition we need is Lewis. But the problem with using Lewis is ranking the acid strength and base strength, because the mechanisms, well, actually the mechanisms are kind of similar. You know, what we do is it's hard to rank Lewis acids and bases because we need hard, soft, right? So what we do is we take a subset of all the acids. That subset's called the Bronsted acid and bases. And that subset, it's very easy to rank them because structurally, it's very simple. What makes a good acid? You know, yeah, proton donor, right? Proton acceptor. The acid's always the same. The acid always is a proton donor. Whereas in Lewis, you know, the acids are all going to be electron pair donors, and they aren't all the same. It's not just always hydrogen. You know, Bronsted is always hydrogen, hydrogen, hydrogen. That's the only thing we're looking at. In Lewis, we have different atoms accepting and different atoms donating, right? In Bronsted, only H is donated, and so the only thing that's different is the base. And so when we look at acid, you know, we got to look at what the base is, the conjugate base, or the anion is.
Would the super acid
There are no super acids on this test. There are a lot of super acids, but we aren't going to deal with those.
but is it Lewis acid?
Yes, the ones you mean. There are super acids in the homework, right? Like, did you see the super acids in the homework? You look. You know, if it's a proton donor, that would be Bronsted and Lewis. If it's just the electron pair acceptor, that would be a Lewis only.
I don't know if this pertains to the test, but in one of the homework questions, they asked us to do like the Lewis structure for CO2 and water combining to form H2CO3, but how is the CO2 pulling an electron pair from the water? Is that why it makes it Lewis acid?
Right.
And then left with, technically you'd be left with like OH, but not.
Actually,
They give you hydronium forms. So CO2 and water.
yeah.
Hydronium in a way, but how?
The CO2 and water is actually one, I think, did I do that one in class? CO2 and water. Well, Lewis, you know, when we look at Lewis,
Yeah.
acids and bases, you know, something like CO2, what we're doing is the base sites are going to have negative charge density in a lone pair. And so what we do is we look at it atom by atom. And so over here, this oxygen should be a base. This oxygen should be a base. That's because this oxygen is going to have a delta minus, right? It's to say delta minus, or we could look at the oxidation states. This is -2, it's got a lone pair. And then this one, this is gonna be the acid site because it's delta plus. Well, a lone pair is negative charge density, and so acids are always going to be delta plus, whatever they are. And the only thing is can it accept an electron pair? And in order to do that, we have to look at it, what we call mechanistically. This is, in organic chemistry, this is how organic reactions get more complicated. And so in organic chemistry, what you do is you look at how, and it depends on what level of detail, Here, what we can say is, if this tries to donate here, because there's going to be an attraction, it's going to be a delta plus, delta minus attraction. And so natural attraction here, but can this carbon accommodate? No, because it would exceed an octet. But what can happen mechanistically is that the PP, and so this could rehybridize from sp2 to sp3 and then accommodate a lone pair out there. And so in organic chemistry, first you look at this, you look at it based on octet and whatever else, and then rearranging. And then as you get more and more advanced, then you get into valence bond and look at the orbitals. And then more and more advanced, you would go to the MOs, molecular orbitals, right? That would be more detailed. And so they look at these on a molecular orbital, like how can the molecular orbitals accommodate those and change in that way?
So one of the questions in practice is, acid has a positive or negative charge density. Well, technically does HCl have a negative charge density and chlorine and positive? So which?
It's both. HCl is both an acid and a base. If you were looking at this in terms of Lewis acid-base theory, it could act either way. This is a base, this is an acid. And the one thing that I wanted to illustrate this by is aqua regia. Aqua regia is, because HCl is, normally people think of HCl as a strong acid. But this is to illustrate that, how, these things react. In aqua regia, when we try to dissolve gold, gold is actually the Ra, and nitric acid is our OA. And therefore, what is HCl? Because what we're going to do is we're going to form gold 3. What we want to form is gold 3 ions. In other words, we want to oxidize it to dissolve the gold in water, and then we can recover the gold 3. And so what is HCl? Does anybody remember? Did I say this a long time ago? James, you remember? Do you remember what the function of HCl is? Is it a strong acid?
Well, it works with the nitric acid to produce even a stronger oxidizing agent, right? Or just it provides extra protons.
Well, actually, nitric is not, because in nitric acid, that would be a pretty good argument, because we need 4 H pluses for every nitrate, and so H plus should be in excess. But in this case, that's not the reason why we add the HCl. The HCl is critical because let's say, you know what, I ran out of HCl, therefore I'm going to dump in extra nitric acid. Then we'll have plenty of protons, we'll just have a lot of spectator nitrates, right? But if you add in extra nitric acid, it's not going to work because the HCl is critical. The HCl you need to do what? What is the HCl acting as?
Lewis acid?
No.
Lewis base?
Yeah, this is base. This is acting as the base. We need base in this. And HCl is the base, not the acid. And so this is why I wanted to show aqua regia, because we get stuck into thinking HCl strong acid. Everybody memorizes it, but here HCl is acting as the base, because why can it act as a base? Of course it can act as a base. It's got lone pairs. Donate it, no problem. It could be a base too. Right? In solution, it's going to be H plus and Cl minus. So Cl minus chloride is the base. And it's a decent base here, but you know, normally when we think of chloride is neutral. But that's in Bronsted. And so Lewis is just much more complex. So how much Lewis do you need to know? Well, what I said was it's too complicated because you need to understand molecular orbital theory. That's why we talked about valence bond or theory and MO theory and Lewis acid and bases. And so it's too much. Hard soft acid base was there's actually a professor at UCSB who came up with it, but at the time when he came up with this, he wasn't at UCSB, he was at Michigan. And he came up with this to make it simpler to predict what's going to be a good Lewis acid, what's going to be a good Lewis base. And what he came up with was a hard soft acid base theory, which is just simplifying it and looking at LCAOs, you know, how atomic orbitals combine to form molecular orbitals. That's all. And so what do I expect? I don't expect much more than that. You know, although I did say something, and did you see the practice test? I looked at that version.
Yes.
Acids have a positive or negative charge. Does it matter what part of the molecule you're talking about?
Yeah, because when we get into Lewis, we look at it atom by atom. So CO2 is both base and acid. Yeah. So if I just had, well, HCl in solution is going to break up into H plus and Cl minus.
Positive.
Yeah, and so acids are always going to have positive. Even here, if I look at a molecule of this is going to be delta plus, that's delta minus. Acids are always going to have positive charge density.
Wait, so then CO2, is it an acid or a base or neither?
Says, which tool is best for predicting all this?
I'm sorry. Let me get the. Yeah.
So in terms of Bronsted or Lewis, I was wondering which would be the most comprehensive information in acid.
Well, Lewis for sure. Lewis for sure, but the whole point of going through all that time talking about MO and all this stuff is to say that even though Lewis is the most comprehensive, it's too much for us, you know, and to predict it. And so this is why you kind of sweep it aside a little bit and then look at just simpler ones like CO2 in water and calcium oxide in water, something like that.
So this question number 2 on your practice test, did you give credit to everyone where it says acids have a blank charge density and the answers are only positive and negative?
No,
It's only positive.
it's only positive. If somebody put negative, I would mark them wrong. Yeah, I'd definitely mark that wrong. Uh-huh.
So what is LCAO and HSAB? We never talked about it.
Yeah, we never talked, it's in Chem 1A is where LCAO is, and HSAB is in a PowerPoint slide long time ago. But LCAO and HSAB come out of molecular orbital theory, and that's just to try to understand the Lewis acid base reaction. That's all. LCAO is not just for Lewis acid and bases. LCAO is for everything. You know, all the chemistry, all molecules, right? All molecules have molecular orbitals. And one way to understand molecular orbitals is to look at how the atomic orbitals combine. LCAO, you know, do you really need that for Chem 1B? No. I mean, I just said LCAO just so you don't forget about LCAO. That's all. Are we going to do any LCAOs? No, we aren't. We're not going to do it. In fact, we have a computer program that'll do it for us. Computer program is called Spartan. You did LCAOs though. Everybody did LCAOs. Take a 1s orbital and a 1s orbital and do an LCAO, and what do you get? You get a sigma 1s and then a sigma star 1s. That's LCAO. That's called LCAO.
Ah, that does ring a bell.
Yeah, it should ring a bell because I think most people have done LCAO, you know.
The hopscotch, the light bulb.
Okay. All right, what else do you guys have?
Number 14.
Number 14, just read out the question.
Which Lewis acid, which Lewis base is stronger, NH3 or both H minus?
Which one did you pick?
Hydroxide.
depends on the acid.
Well, hydroxide's up there. It's much stronger. But you know, this is not a subset. If I asked you which Bronsted, which would be a subset of all bases, then you would say, oh, Bronsted base, it would be hydroxide for sure, because the acid's always the same. But here, the acid can be anything. If the acid can be anything, then all of a sudden, do you know which one? No, because it depends on the acid. What atom is the acid? It's not H+, or it might be. And so the whole point of doing that is, well,
So we want the right answer.
It's not
C,
depends
depends on the acid.
depends on the acid.
Or number 15.
But why though? Why wouldn't hydroxide be a stronger Lewis base?
So like water.
Because of LCAO. We don't know what orbital that's combining with. Uh-huh.
And for the highest pH possible,
Let me talk about, you know what LCAO is, right? Let me just say one more thing. You know what hard soft acid base is? HSAB? HSAB is LCAO looking at this. If I take an S and a P, you know, then we're going to get some kind of MO, right? But they're two different. Let's say this is a 2S, but if I take an S, 1S, and a 4S, are they going to form, you know, in terms of valence bond, this would be pretty weak overlap, but here, we call this hard, 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 soft. If I take this is a 4S, I mean a 4P, sorry. If I take a 4S and a 4P, ooh, that's good. That's a soft, soft. And so when I make my MO, it's better. This is why things like heavy metals, you know, heavy metals like sulfur more than oxygen, because sulfur is soft. You know. Oxygen's a lot harder. Anyway, was there another question? Because we're out of time, but I can stay.
The one concerning the Bronsted subset, how would you be able to
You look at the chart.
straight up off the chart?
Yeah. You look at the chart, or unless you know structure
Right, I'm just kind of
and properties. But we talked about structure and properties in Chem 1A. I'm not sure how much people remember from that, but we're going to talk about structure and acid strength when we do the lab later on. Yeah, but some of it's easy because, yeah, but you find patterns in the chart. The patterns in the chart would be like this. What's a stronger base? This you don't even have to look in the chart. You should be able to know. Yeah, there's certain patterns you see in the chart that you can determine.
Ionization, would that be inherited by stoichiometry? That's kind of a simple question. Like, if you had like a 13%
No.
ionization, like 2 of them, would it be a 26%?
Oh, well, it wouldn't work that way, but it would affect. Yeah, but it wouldn't work that way. Yeah.
I have a question. What about number 17? Like, what is the first thing we should do for it?
You do the one with the biggest K and then work down.
Okay, so we can, okay, so it's not gonna be simultaneous?
It might be. You have to show that it is.
Okay.
You can't just say it's
Okay,
simultaneous.
we have to show first.
You have to show it, and like I said earlier, we just try it stepwise. If it fails, then right. If it doesn't fail, then it works.
Okay, perfect, thank you so much.
For the pH, it can go up all the way as much as you want it to, but then not infinity. That's fine.
No, you're gonna reach a certain thing, like solubility and then non-ideal effects. So it's going to increase, but it doesn't increase like normally. It would just dramatically tail off. You know, yeah.
And even with the negative too, right? It will go with that, but it will.
Right. It's gonna have to tail off because you're gonna reach a certain limit where you can keep adding, and because the ion pairing and other stuff is going to prevent it from it. So.
Professor, this one I found really weird. I thought this was gonna be the base, this was gonna be the acid. I mean, I did the little acid, the little structures, and this one turns out to have a lone pair. But maybe that's not the one that's bonding, or?
Yeah, the lone pairs are on oxygen as well. On this. And so you had this one as the acid, this one as the base?
No, so this is correct, but I had this as the acid, and this is the base.
The only thing that could be acidic here is the sulfur, but is sulfur capable of accepting versus here? If you look at the oxidation states here, I would do that and look at how the oxidation states are. You put this one because the sulfur oxidation state's quite high? Is that the reason why?
No, I put this as a base because of the lone pair on S. So I thought the lone pair was.
Oh, okay. I see what you're saying. Yeah, you know, it could be both.
Could be both.
That's why when we did the CO2 and water, we did it both ways. We did CO2 as the base, and we did CO2 as the acid. So you're fine there, but you just look at, you know, what can form. And
So I would look at this one and see that this one doesn't have really any acid properties.
Well, no, barium doesn't, but sulfur does. In that.
Well, so then how is it a base? Which one's the one giving it?
No, because you know, sulfur is +6 here, so maybe the sulfur itself, but you gotta look, you know, how can sulfur accept a lone pair from a base? Mechanistically, you know, with rearranging electrons and everything else. Can it? You know?
Okay.
But, and so, you know, that can act both, but what we do is we look at, you know, what the products that form from this are. And then,
oh, it's SO3.
oh, is it SO3?
Yeah.
Oh. And this has a lone pair too.
But it's with barium. Barium doesn't,
No, barium doesn't do anything. Barium's a counter ion.
Okay.
Barium's not bonded to it.
Okay, there it is. Yeah, that makes sense. Okay.
This is the ionic compound.
Yeah, that makes sense. Okay. Okay.
This might have trouble because, you know, something.
Yeah, that one's the base. That's good.
Okay.
That one's the donor. Okay. Thank you.
Yeah.